We're exploring the fascinating complex of volcanic and other igneous rocks that make up the St. Francis Mountains at the heart of the Missouri Ozarks. Here, you can see the exposed remains of massive eruptions, and explore a set of related intrusive igneous rocks with a complex story to tell. These represent one of the best exposures of Precambrian rock in the central United States, and certainly within the Ozark region of northern Arkansas and southern Missouri. We spent a week exploring this geologically distinct area, emphasizing sites within the region's extensive public lands, where you can examine intriguing volcanic deposits and get close-up looks at ancient magma chambers and other igneous intrusions. But what were these volcanic eruptions like? Did they feature free-flowing lavas like those we see today in places like Hawaii? Were they more reminiscent of explosive eruptions like Mount St. Helens? What about the supervolcano at Yellowstone? Or perhaps something else? We've been disturbed by how many public resources convey misleading or outright wrong information about St. Francis igneous history. So follow along with us here on Ozark Outsider as we continue our series on Ozark geology by exploring this region's complex igneous past. Here at Johnson Shut-In State Park, the Black River carves a narrow gorge through a thick sequence of volcanic deposits. Most of the rocks here, and indeed most of the volcanic rocks in the St. Francis region, represent what are called ash flow tuffs or Ignimbrites. These are deposits that resulted from explosive eruptions when massive clouds of superheated gas, ash, and other debris raced across the landscape. To us, the feature that best illustrates the violent nature of these eruptions are these lapilli, essentially volcanic hailstones. As the classic paper describes them, they are believed to have agglomerated in midair during eruption, and then to have fallen like a rain of hail to become incorporated in the gaseous cloud. This beautiful deposit is about 25 feet thick, part of a broader unit of ash flow tuff around 65 feet thick. Think about the scale and violence of volcanic eruptions needed to produce just this one unit. The famous Roman-era eruption of Mount Vesuvius buried Pompeii in about 20 feet of ash, and nearby Herculaneum in more like 60 to 80 feet. That depth is matched by just this one cliff, formed by the unit containing the lapilli, which represents a small fraction of the total depth of volcanic deposits in this sequence. As it turns out, geologic mapping here has documented at least 12 different units within a sequence around 2,000 feet thick. And this is a good place to note that, while this video emphasizes features you can see on the ground, the interpretations we present draw upon decades of scientific studies that have utilized microscopy, radiometric dating, drill holes, and more to piece together a more complete story. For example, we can't determine the age of these rocks just by looking at them, but radiometric dating has identified a clear period of regional igneous activity, including volcanism, lasting about 30 million years, from 1.48 to 1.45 billion years ago. Lower in the sequence at Johnson Shut-Ins, you can find something quite different, what appears to be a fine-grained siltstone. And just a bit further down is probably our favorite rock at this site, a beautiful conglomerate composed of semi-rounded chunks of volcanic rock suspended in what looks like ash and maybe silt. Deposits like these suggest short sedimentary interludes between multiple eruptions, when water flowed across and pooled on the landscape, eroding, transporting, and redepositing recent volcanic material. Regionally, there's a lot of extrusive rock that fits in the ashflow tuff Ignimbrite category, including exposures at Bell Mountain, Shepherd Mountain, Knob Lick, Royal Gorge, and Taum Sauk Mountain. And while many of these outcrops can be somewhat featureless close-up, others display some pretty cool textures. At this road cut, the paler streaks have been interpreted as crushed pumice fragments incorporated into the ashfall. You can tell geologists like this one by all the sampling holes bored into it. While field geology is clearly interesting, lab geology is more boring. While the vast majority of volcanic rocks in the region are some form of ignimbrite, features suggestive of actual lava flows can be found on Russell Mountain. Here, outcrops display what looks like flow banding and other especially lava-like textures, though one source suggests we might be looking at a near-surface vent here rather than an outright lava flow. And here at Hughes Mountain, these spectacular honeycomb patterns at the summit are called columnar jointing, a feature commonly associated with lava flows. But there's a catch, and to understand it, we need to talk about the composition of these rocks. The lava most people are familiar with is the runny, free-flowing Hawaiian type, which has a low silica composition geologists classify as mafic. Columnar joining is very commonly associated with this composition, especially in a certain rock type called basalt, to the point that columnar jointing and columnar basalt are often used as casual synonyms. In contrast, a higher silica felsic composition makes molten rock much more viscous. You may need a time lapse covering weeks or months to really appreciate the behavior of felsic lava, which has even been compared to glaciers. Most volcanic rocks in the St. Francis Mountains have a felsic composition geologists call rhyolite. Columnar jointing generally isn't as common in rhyolitic lava flows, though this example from Yellowstone shows that it can occur. Columns can also develop in rhyolitic ash deposits, as in this example from Hong Kong. So, while it's easy to see columns and assume lava flow, it's not entirely clear to us what the complete story is here. Regardless, these columns are spectacular and unusual features within the broader St. Francis rhyolitic volcanic terrain. And this reinforces the point that unambiguous lava flows in general are uncommon here, relative to the massive deposits of Ignimbrites. So let's revisit our opening question. What kind of volcanism was happening here? Let's consider two of our opening examples of volcanism. We now recognize that mafic lavas tend to be free-flowing, while felsic lavas are much more viscous. But the corollary to this is that felsic magmas don't tend to produce as much proper lava at all, because that thick molten material tends to plug up the subsurface plumbing, building up pressure that releases all at once in catastrophic explosions that produce massive ash deposits instead. Sound familiar? So Mount St. Helens does seem a better match for the style of volcanic eruption preserved in these deposits. But is this the best regional analogy for the St. Francis Mountains? To answer that, we'll need to shift our focus from the extrusive volcanic rocks and start looking at the intrusive igneous rocks beneath them. Let's take a quick pause in this eruption of geological awesomeness to note that these videos take a lot of time and resources to produce, and we appreciate the support from everyone who likes, shares, and subscribes. If you're able to provide financial support, you can make an easy one-time or recurring contribution via Ko-fi, linked in the video text below. And now, back to the rocks. Here at Amidon Memorial Conservation Area, we find the Castor River carving a gorge through beautiful pink rock, whose fairly coarse minerals provide a hint at its origin. Igneous crystals grow slowly as molten rock cools, so their size here tells us this is an intrusive igneous rock that solidified underground rather than being erupted onto the surface. This is granite, a high silica felsic rock chemically similar to the rhyolite we've already seen, and that's not a coincidence. This rock dates to the same period of igneous activity as the widespread volcanism, and may represent an example of the magma chambers that were feeding those massive regional volcanic eruptions. It's pretty cool to be able to visit volcanic deposits and subvolcanic plumbing systems all in one region. By this point, you may be wondering, what did all this igneous activity erupt onto and intrude into? What was the pre-existing older bedrock that geologists call country rock? To answer this, we need to find something clearly different and older than the interrelated volcanic and granitic rocks that all date to the same period. And the closest thing anyone has found is a small but distinct exposure of crystalline rock at Hawn State Park. This is granodiorite, a felsic rock broadly similar to granite, but subtly different in ways that matter to geologists. For example, you might be able to convince yourself that the granodiorite has a higher percentage of dark mafic minerals than a typical granite also found at this site. What we want you to look at is a textural feature. Can you see a linear trend in the minerals? A sort of light banding running this way? Some geologists have interpreted this subtle banding as a sign of metamorphism, arguing that this is actually a rock called gneiss. Gneiss, pretty much by definition, has undergone alterations from heat and pressure that realign the rock's original minerals into linear bands. For example, this rock from Wyoming's Bighorn Mountains is really nice. And since nowhere else in the region do we find anything remotely gneissic, and the granodioritic composition is also distinct, the argument goes that this must be a rare example of pre-existing country rock. On the other hand, this subtle texture could also represent what's called flow banding, essentially a remnant of convection currents within a cooling magma. Moreover, dating places this rock's formation into the same time window as the predominant volcanic magmatic activity. So we came here looking for metamorphic rock, and this is about as nice as it gets. Whether or not this is true country rock, the point is that there are few, if any, examples in the St. Francois Mountains. The sheer scale of extrusive and intrusive activity, along with subsequent erosion, have all but wiped out evidence of whatever was here before. The summit of Knob Lick, with its iconic fire tower, is capped by outcrops of volcanic rocks from a regionally widespread formation, the grassy mountain Ignimbrite. However, at this nearby exposure, we can see granite clearly intruded into the overlying volcanic rock. For example, a close look shows pieces of Ignimbrite suspended in the underlying granite. These must have cracked off and dropped into the molten magma as the latter ate its way up into the already solid volcanic rock. The clear implication here is that this granite has to be younger than the Ignimbrite it's intruding. To really understand what's happening here, we need a better view of the regional landscape, and there's only one way to get it. I'm not a big fan of climbing old towers, but the things we do for this channel. From the Knob Lick Tower platform, we can look out to the southwest over a broad expanse of low, gently rolling terrain known locally as the Flatwoods. Beyond this is a distinct ring of hills mostly encircling the basin. The basin itself is underlain by a subvolcanic granite similar to the rocks we saw at Amidon. And while those hills are mostly kept by volcanic deposits, they also include a set of so-called ring granites that intruded along narrow belts surrounding the broadly circular subvolcanic granitic mass. Knob Lick itself is part of this pattern, a valley floor of subvolcanic granite overlooked by a 400-foot hill composed mostly of ring granite and a veneer of Ignimbrite. All of these rocks date to the same overall period, but why would a narrow belt of granites intrude around the perimeter of a slightly older granitic mass and up into the overlying volcanic rocks? With typical felsic volcanoes like Mount St. Helens, there's, well, a volcano, with a basic structure that might look something like this. A magma chamber intrudes some pre-existing rock and erupts repeatedly onto the surface, depositing volcanic debris that builds a distinct cone-shaped edifice. But we don't see evidence for substantial volcanic peaks in the St. Francois region. What we do have is signs of something even more dramatic, a caldera. Calderas are large collapsed basins formed by volcanic activity on a grand scale, like the famous Yellowstone caldera formed by a massive eruption event 631,000 years ago. In this graphical sequence of the Yellowstone caldera's formation, multiple regional eruptions are fed by underlying magma chambers. At some point, a single massive eruption empties a magma chamber to the point of instability, causing the overlying bedrock to collapse into the voided space along a series of faults ringing the area. The result is a massive basin, the caldera, often with a distinctive rim. And magma may continue to intrude upward along the newly created faults, sometimes reaching the surface as new volcanic activity. A similar process formed a caldera that underlies the Flatwoods Basin, overlooked by Knob Lick, though some details differ. In this case, long erosion has exposed much deeper portions of the caldera, revealing the underlying granite. Volcanic deposits around the rim and beyond have preserved evidence of massive eruptions, and ring granites have intruded up into the volcanic rocks along faults ringing the collapsed caldera. And if that wasn't cool enough, it turns out the geologists have mapped at least 3 overlapping calderas within the broader St. Francois Mountain region. Although these ancient structures are now highly eroded and not as scenically dramatic as Yellowstone, it's still astonishing to recognize that the shape of the regional landscape today still reflects igneous activity from well over 1 billion years ago. That view and realization is worth a climb up a rickety tower. So far, all the rocks we've looked at are pretty similar compositionally. Whether volcanic rhyolite or intrusive granite, they've all been high silica felsic rocks loosely related to one another. But here at Silver Mine's recreation area, an old dam on the St. Francis River marks the location of a very different geologic feature. Most of the rock behind me is the pink-gray Silver Mine granite, but cutting across it here is a linear feature of a dark, very different kind of rock. This is a dike,
where younger igneous material intruded into older pre-existing rock.
The Silver Mine granite happens to be another ring granite intruded along the edge of the caldera we just talked about. But compare its typical appearance to the dike rock, which looks utterly different. This is our first local look at basalt, that typical low silica mafic rock with a very different mineral composition. Dikes like this typically form when molten rock intrudes through cracks in existing hardened rock. One way we can prove that is to compare the texture of the basalt at the center of the dike, where the crystals are relatively coarse, with that at the edge of the dike, where it comes into contact with the granite, and where the crystals are much finer. This is what geologists call a chill margin. As the hot molten basalt was injected into the relatively cold granite, the edges cooled off quickly while the center stayed hot longer, growing larger crystals. For another example, this geologically famous road cut along Highway 72 near Fredericton exposes another large mafic dike that appears on both sides of the road. We'll actually be revisiting this site in the next video for a very different reason. Did any of these minor mafic intrusions reach the surface as lava? We followed a couple of leads, but exposures were unconvincing or inaccessible on this trip. We'll just say that although exposures of mafic rocks in the St. Francois Mountains are few and far between compared to felsic ones, it's worth knowing that rocks of varying composition are part of the broader story. So far, this has all been pretty academic, but now it's time to get economic on an early morning hike up Shepherd Mountain. This is yet another thick volcanic sequence with classic views across igneous glades and plenty of neat textures. We think these are more crushed pumice fragments. But near the summit, we find one of the old open-pit iron mines on the mountain, where the iron-bearing mineral magnetite is present in concentrations sufficient to flip a compass. Or just try lifting a remnant chunk of ore, and you'll be convinced of the high iron content.
That is a heavy rock.
Directly across a narrow valley is Pilot Knob, with a much larger iron mine at its summit. The iron resources here, and the associated railroad connecting them to St. Louis, were important enough to shape an influential Civil War battle centered on nearby Fort Davidson, now a state historic site. Elsewhere, just across the St. Francis River from that dam and dike we visited earlier, an easy hike leads to the Einstein Silver Mine, where silver, lead, and tungsten were once extracted from extensive underground workings. Old tailings piles still hold interesting minerals.
There are some cool quartz-lined bugs in here, and some purple fluorite, the first time I've ever found that in the wild, and some shiny metallic cubic minerals like galena and pyrite, and some other really cool stuff.
So, how did these unusual mineral resources get here? To briefly summarize a complicated reality, these are hydrothermal deposits, meaning that deep groundwater superheated by magmatic activity became enriched in certain elements derived from that magma, then carried them upward along faults or other pathways through the overlying rock, eventually depositing them in concentrated veins or other structures. And the resulting rich Precambrian mineral deposits, once discovered and exploited, played a significant economic role in the development of the St. Francis region and even St. Louis. This hydrothermal legacy might again bring Yellowstone to mind, since that region's hot springs, geysers, and fumaroles are globally famous. But the present Yellowstone caldera is quite young in geologic terms, and it remains very much active. In contrast, any igneous or related hydrothermal activity in the St. Francis Mountains ended well over 1 billion years ago. Let's also consider a size comparison. The crater on Mount St. Helens is only about 1 mile across, while the present Yellowstone caldera is 30 to 45 miles across. So is there a just right size comparison for the roughly 13-mile wide caldera we saw from Knob Lick and its similarly sized neighbors? Let's consider the Valles caldera in New Mexico, which at just under 14 miles wide matches up nicely with the St. Francis Mountain calderas. Valles, like Yellowstone, is also much younger, with its most recent eruption only 1.2 million years ago, but it provides a better visual comparison for calderas of this size, clearly displaying the classic central basin and surrounding rim. While Valles is a decent size analog for the St. Francis Mountain calderas, their relative tectonic background is quite different, but that's another deep dive we are not going to attempt here.
We've focused on these calderas because of where the ancient igneous rocks are exposed at the surface. The actual region of volcanism extended well beyond these, but most of the evidence has been deeply eroded and/or covered by younger sedimentary rocks.
And while the Valles Caldera is an official national natural landmark managed by the National Park Service, the St. Francis Mountain calderas are just sort of hidden in plain sight, underappreciated, like most Ozark geology. But if there's one place in the St. Francis Mountains that isn't underappreciated, it's our next stop, arguably the region's most famous and popular geologic site, Elephant Rock State Park, where a classic Missouri pink granite has been weathered into fantastical shapes that early visitors thought looked like pachyderms. So far, all the granites and rhyolites we've been describing here have been dated to that single period between 1.48 and 1.45 billion years ago. But the granite at Elephant Rocks, while it looks pretty similar to the rest, is noticeably younger, dating to around 1.3 billion years ago. This rock represents a second pulse of magmatism that intruded all the other rocks we've been looking at. And it's not just Elephant Rocks.
Geologists have identified and mapped at least 10 distinct plutons, or magmatic bodies, that date to this later period. Despite the age difference, the granite here shows a lot of the same characteristics as its older cousins.
Like the hydrothermal minerals we talked about earlier, this granite has historically been an economic resource for the area, long quarried as an attractive building stone used extensively regionally, even forming the base of piers for the famous Eads Bridge across the Mississippi River in St. Louis. It's great fun to explore the volcanic past here, and try to comprehend the extraordinary amount of energy once released across an ancient landscape. We hope we've convinced you not to envision runny basaltic lava flowing merrily across the landscape, or one pointy volcano towering over the landscape, or even a single super eruption. Instead, wrap your head around a series of overlapping calderas anchoring a 30 million year period of catastrophic volcanic eruptions blanketing the regional landscape in over a vertical mile of debris. Over an even broader period of time, magmas deep below formed overlapping granitic plutons, intruded thin dikes of mafic basalt into the overlying rock, and even sent veins of superheated mineral-laden water snaking toward the surface. And even after 20 plus minutes, this is still a wildly simplified presentation of the much more complex geologic reality. There is so much more opportunity for exploration, discovery, and interpretation of the St. Francis Mountains. But for now, our Geology of the Ozarks series has to move on. In the next chapter, we'll start leaving the Precambrian behind.
This conglomerate of boulders and cobbles that grades up into finer sandstone represents the onset of younger sedimentary deposition on an ancient landscape.
Stick with us as we head off in search of the great unconformity in Missouri, at great personal sacrifice.
It's February and this water is freezing. Things we do for geology.